Alright, physics. We were doing review, took a quiz today. I just want to tie up a couple of loose ends here in forces, just as, like little last second things. They might come up at some point in the future. If they do, I'll go over some specific examples then. I just want to make sure that I mention them out loud. Um, they're not super difficult concepts. I think they're all things that we've talked about on some level. Um, it's going to have a little bit to do with trig. Again, I apologize for that. I trust that you can handle it. Stick with me. I'll work with you. All right. Now, I'm just gonna go off to the side a little bit here from where we left off with the review. So I'm gonna call this forces loose ends, right? Because yeah, I just want, like I said, I want to cover this. Now, one of the loose ends I want to talk about with forces is how to kind of combine forces, and we talked about this a little bit with the Pythagorean theorem when we talked about what do I need to create equilibrium between 20 newtons north and 20 newtons east, right? And the way we figured it out was we knew that it had to point southwest and it had to break up into something that was 20 newtons south, like that, and 20 newtons west, like this. And the way that we figured out, like, how big is this, is by doing Pythagorean theorem, right? Some a squared plus b squared equals c squared stuff. So 20 squared plus 20 squared equals c squared, which means 800 is c squared. So c was about 28 newtons, right? And that's how we got that last side. That works for basically any combination as long as they're at a right angle. So if you have a 5 Newton force east and a 12 Newton force south, that should be a comma. What is the resultant force? Right, and this term, the resultant force, is, I'll make a diagram, right? So I have a 5 newtons, let's say that this is 5 newtons east, and then I have to go 12 newtons south, right? This is 5 newtons, oh, let me not put the directions, you can see what direction they're going. So 5 newtons east, 12 newtons south. The resultant force, right? So what this means is go from beginning straight to the end. What I mean by that, we started right here, and I'm going to draw a line straight to the end like this. So this right here is my resultant force, going from here straight to where we end up. If I had to replace them both with a single force, instead of going east and south, if I wanted a single force that kind of pointed southeast, how big would it be? What is the resultant force? So in order to do that, right, south and east make a right angle with each other, which means I'm going to do 5 squared plus 12 squared equals, I'm going to call it r for resultant, r squared. Let's call it r. This is 25 plus 144. That equals r squared. So 169 newtons equals r squared. Actually, newtons squared. I'm going to leave that off for now. Hey, can we cooperate, please? There we go. Cool. Good. Thank you. And I actually know this one. This is a nice one. This is a perfect square. R equals 13 newtons, right? The magnitude is 13 newtons. The size, right, of that arrow, the length of the arrow is about 13 newtons. Is exactly 13 newtons. And the direction is southeast, approximately, all right? But this is a resultant force. What is the resultant force, right? The second piece to resultant force, I guess I can go this way a little. Oh, I can't go that way too much. So I guess I'll go... Computer? Hello? Are we cooperating? Are we good? Cool. I'm going to use those same numbers. If you have a 5 Newton force and a 12 Newton force, what is the largest possible force you could make? What about the smallest? Right? So I have a force that's 5 newtons. And I also have a force that's 12 newtons. Right? What's the biggest force they could possibly make? Well, if they're both pointing the same way, they're going to combine to be as big as possible. Right? So if I add them both, 5 newtons plus 12 newtons would be 17 newtons. That's the largest. Right? Just straight up add them in the same direction. If I wanted them to be the smallest, right, what's the smallest force that I can make? Then I need them pointing in opposite directions. So instead, let's say that the 5 Newton force is going this way, the 12 Newton force is still going this way. Well, that would be like negative 5 newtons plus 12 newtons, right? And that's only 7 newtons. That's the smallest possible force I can make. You know, I think, well, what if it's 5 and then negative 12, Kalimlin? I mean, that's negative 7 newtons. It's still a magnitude. The size is still 7 newtons. We're arguing over the direction, right? I'm arguing over is it going one way or the other way, but it's still only 7 newtons. All right, so I can make a 7 Newton force if I point them exactly opposite directions. It should kind of track, it should kind of make sense that I can make any force in between those. So I can make something as big as 17, I can make something as small as 7, and I can make anything in between those. I'm not allowed to make anything bigger than 17. I'm not allowed to make anything smaller than 7, but I can make any number I want in between those if I put them at some angle. We just found I can get a force of 13 if I make a right angle between them. If I call this 5 newtons and this 12 newtons, then this resultant, right, we already said that that side would be 13, and that fits right in between these two. So again, I'm just kind of like loose ends. I didn't really know how to classify this, but there's a potential that I might ask you in the future, right? What's the biggest or what's the smallest? Which of these forces could you make if you have these original forces? And it just has to do with if you add them together straight up, that's the biggest thing you can get. If you subtract them from each other, that's the smallest thing you can get. The last little loose end to look at has to do with equilibrium again. Now, equilibrium said that all the forces in all directions, right, the net force adds up to equal 0 because they cancel each other out up and down, they cancel each other out left and right. I'm going to take a situation where I have a person who is dragging a sled because it's winter and we like that kind of stuff. So they're dragging the sled at an angle, right? I'm going to call the angle 30 degrees. I know it doesn't look like 30 degrees, but I'm going to call the angle 30 degrees. So let's say that they're pulling like this, right? Here's their force. They're pulling with a force of 10 newtons. And they're pulling with a force of 10 newtons at a 30-degree angle. Right, so a student pulls a sled with a 10 Newton force at, oh, just kidding, at a 30-degree angle from the ground. Well, I'll say from the horizontal. It's not necessarily from the ground, but it's from the horizontal. if the student is pulling at a constant speed, student pulls at a constant speed, then what is the force of friction between the sled and snow? Right, now normally to do force of friction, you would do this. Force of friction is mu times the normal force. But I told you nothing about the sled. There's no info on the sled. Which means I need to use the fact that this thing is moving at a constant speed, right? Because constant speed means acceleration is 0. And if the acceleration is 0, that means that the net force equals 0. And if that's true, right, that's equilibrium, which means if I draw my picture, right, if I draw a picture of the sled, if I draw a picture of all the forces, then I'm going to simplify the sled into a dot. That means that I have this force, which is 10 newtons, at an angle, at a 30-degree angle, that we're moving this way, I guess, if I'm going to match up with the picture, which means that I have some, right, force of friction here. I also have a force of gravity. But it means that this force right here is balancing out these other two forces. This is going to move up in a second. My computer's freaking out a little bit over something. I'm going to try to figure out what. Okay. Can we freak out less, please? That'd be pretty cool. Okay, thanks. So it means that this 10 Newton force at an angle is perfectly equaling these other two forces. Which means if I take this force and I split it up, so if I take that 10 Newton force and I split it up into a horizontal piece and a vertical piece, and again this is still 30 degrees, then this horizontal piece should be the same as the force of friction. Which means if I can find this horizontal piece, if I can find this side of the triangle, then I also find the force of friction. Right, so I know that cosine of 30 degrees is equal to the adjacent side over 10 newtons. So 10 newtons times the cosine of 30 degrees equals the adjacent side, and that means that it is, oh boy, math. I don't know math off the top of my head, but my calculator does. 10 times the cosine, nope. Oh man. It's 8.7. Had to do some math there, apologies. What that means is that it's 8.7 newtons, right? So this side here is 8.7 newtons, and because we know it's moving at a constant speed, which means there's no acceleration, which means net force is 0, which means equilibrium. Because we know all of this, if I solved for this part, then I also solve for the force of friction, which means that the force of friction is also 8.7 newtons. Right? I know it's a little weird to like look at and think about, but given what we know about equilibrium, given that we know equilibrium means all the forces equal 0, well, so all the left-right cancels out, all the up-down cancels out, that means that if we can't find something in particular, you should be able to find like the opposite, and it will help you figure that out. All right? Now, we're not going to do much more with forces, but next class, which is like either C day or D day, depending on which group you are, I'm going to start talking about something new. I'm going to try to figure out how to do a lab in the very near future, just because we haven't done one, and it usually helps things make more sense. But this was just tying up loose ends. I would maybe like go back, watch this again, take some notes on it, because I'm not going to talk about this again for a while. We'll start something new soon. I'll grade those quizzes as soon as I can. In the meantime, be good. Stay safe, kids. I'll see you soon.